Hello everyone, I'm Fan Mo from More Threads R&D. I'm gonna talk about this compression toolkit that is based on torch.fx and torch MUSA. So the talk will be within 10 minutes and consists of these 4 parts. First, we'll have short introduction of the torch MUSA, and then we have a little walkthrough of the PyTorch.IR and some quantization methods that PyTorch has provided. And then we're gonna go deeper into our NeuroTrim and what it is and how it works. And finally, we're gonna share about some future works that we're gonna do and some expectations of the PyTorch. Okay, let's get started. So some of you might have known that the More Threads has released the MUSA, which is a meta computing unified system architecture. Well, it's quite similar to CUDA. Like we provide in main libraries as CUDA does. As you can see from the figure that we provide the MUSA runtime, MUSA MUDNN, MUBLAS, and MCCL for communication as well. So if you are proficient in CUDA programming, it will be easy for you to transfer to our MUSA platform. On the other hand, the Torch MUSA is kind of like a plugin for PyTorch that enables the PyTorch runs natively on our MUSA platform. And by using Torch MUSA, you can have almost the same user experience as PyTorch it is. You can just simply modify the backend string from the CUDA to MUSA and run it is. And also we have some features and operators that are highly optimized, especially some GMM kernels and attention kernels. So if you're running on large language models, we're gonna have some high performance. And last, we have some more customized features, especially on the field of the quantization, which we're going to talk about later. And before we go into the compression toolkits and the NeuroTrim, we have to have a little walkthrough of the PyTorch IRs that PyTorch has provided. Well, as you know, during all the years of the PyTorch, it provides many IRs, like from the early stage, we have torch script, the JIT.script. And from the PyTorch 1.8 or 1.9, I guess, we have the FXIR, and it's widely used until now. And from PyTorch 2.4 or 2.5, we have the ExportedIR from the export program, and also the AOT AutoGrad IR that used for training. With all these IRs, the PyTorch has provided 3 ways of the quantization, that they are the eager mode, and FX mode, and the PT2E mode that we can call it the export mode. So among all these options, some might like to ask what the best way of the IR tracing. Well, I read this phrase like months ago in the PyTorch forum. I cannot find the page right now, but it do say what I like to say. Just there's no best way of IR tracing. There's just trade-offs. So what's the trade-offs? I think it's just we don't have to take a specific one way of IR tracing. We can have both of them, or we can have them all. Then we move into our NeuroTrim and see what the trade-off that we made. As we all know, if we would like to quantize a model, well, it's be important for us to have the full graph, a full model graph, right? Something like the OpenVINO and MNN, they have their own IR definition, but we like to do it within the PyTorch itself. So so we chose the FX as our IR. And why FX based? Because there's three reasons. That first is debuggable. Like we can easily add some PyTorch hooks or just running with the PDB to check the input and output values from each node. And secondly, we can easily modify the graph or the subgraph when we do the quantization. And last, it's very easy to integrate with other frameworks or even with PyTorch itself. Like we can do PTQ or update the weight during the quantization. And as you can see from the picture that the NeuroTrim just only take one PyTorch model and one configuration in, and it outputs a PyTorch IR that we can send it to the inference engine. And inside the NeuroTrim, the first stage we call the IR tracing stage. That's the trade-off we have made. Like we took many ways of IR tracing. Like we have symbolic trace, we have dynamo, we have export. It's kind of like a fallback mechanism. If one way is failed, then we move to another. And after the tracing stage, we can have the whole model graph. Then we can move to the optimization and the MUSA lowering, which is a backend specified. Well, for the optimization and the MUSA lowering, we're going to share about some customized optimization that we have done. First, we have some customized kernel fusion. From the right figure, you can see that we have the convolution come up with the batch norm and then come up with the CLU. And this can be easily found in the model of YOLO. And we can run it with just a single kernel and it runs, so we can get higher performance. And more of that, we have some customized weight update. Well, it's not like a PTQ or some fine tuning. It's just update the weight on the fly, like the bias correction or the GPTQ for the large language models. And most importantly, you have some many D types supported, like except the integer 8 or integer 8 or int 4, we have floating point 8 supported. That is cannot be only used for the large language model, but we can apply it to some CV models, so we can have the high performance and good accuracy. Well, last I'm going to share some future works that we're going to do. The first is that we are trying to make the large language models and the vision language models that are traceable. Now, if we like to have the full graph of something like DeepSeek R1, it will be very hard, and it's hard to, for us to do some optimizations. So we are trying to make that doable. And also, we are trying to accelerate the quantization. Since we have tried to quantize the DeepSeek R1 671 billion model, and it took our days, and it's easy to to throw some errors. So we are building a fault tolerant system that can restart the quantization from some checkpoint. Well, last I'm going to share some expectations of the PyTorch. First, since we are using the symbolic trace and the dynamo and export, we hope we can have less graph breaks. Since every graph breaks will bring more optimization works, and so we hope that we can just run the model smoothly with one graph. And last is we hope that the PyTorch has support more floating point 8 operators, since the P8 now can only be used of the GMM in PyTorch now, but we think the float 8 can be treated like the float 16 or B float 16, so we can add more optimization in it. Okay, that's all I would like to share. Thanks.